concept that, okay, if you are, first of all, what is the limitation of resistive load we have discussed yesterday, because there is a limitation of the swing. The moment you try to increase the gain and use large RD, the swing suffers. We are not able to get proper swing, although you are getting good gain, but the available swing will go down. So now we use current source load, which can basically achieve both high swing as well as high gain. Uh, and then we in this lecture, the difficulty in DC biasing is mentioned, that in this particular configuration, if you're using a current source load, how the DC bias point is very sensitive to the device parameter variations. So this is what is discussed in this one. And then you have the, so after discussing the DC biasing difficulty, some small signal analysis, I think it has been done. And the overall small signal gain has been calculated. The concept that why there is a gain coming, what is the main reason for a large voltage gain, those things have been discussed. And also maximum swing consideration, that as compared to the DC bias at the gate and the DC bias at the gate of PMOS, NMOS, what is the output swing maximum, that has been discussed. So this much, I think it is for the active load, whatever has been discussed, it is pretty straightforward. The DC bias and the swing. That's what I can see in this lecture. And in the previous lecture, the lecture number 7, I can see there is some discussion on the small signal frequency response that we were discussing yesterday. So here in this lecture, we have the same discussion that we did yesterday. We were beginning this discussion, and I was trying to discuss the board plot, how it comes, and what kind of simplifications we can make. So this Miller effect, the Miller theorem, has been discussed in this lecture, and how do you break down CGD so that you have this kind of configuration where after each stage you have just the capacitance coming between the nodes and the ground. So if you have capacitance coming only between the respective nodes and the ground, then the analysis becomes easier. That's what has been discussed in this. And then the corresponding board plot, how do you derive, that has been discussed. So this, to some extent, we completed this yesterday also. And then I think some noise analysis has been done, the derivation of the output noise and also the input referred noise, both the things I think has been discussed. So till this point, if you have done 7th and 8th, I would like to know if you have any doubt on 7th and 8th, because most of you have completed these two. So let me know if you have doubt in these two.
So in the noise analysis part, like in the small signal model, we are dealing with the power of the noise, like power of the signals. But then can we apply KCL, like in the small signal circuit, like we applied KCL and we found out the input reference noise and V on. Can we do that?
So ultimately, you're looking at the Vn square, right? So if you're computing the output noise voltage, which is basically taken by the total small signal current, which is In square multiplied by the Ro square, and then you divide by Gm square to get the input referred noise. What is the problem in that? So once you have the output referred noise, you divide it by the gain and get the input referred noise. And the way we get the way we are getting the output referred noise is that any circuit, whether it is a resistive load or active load, if you have a resistive load, so if you have a resistive load, you take the power current, or basically the noise power current of the resistor as well as the MOSFET, get the output voltage because of them, and then basically, because you are going to sum up the power, you're not going to sum up the current, you're going to sum up the power. So following that concept, we get the net power, net output noise power, and input referred power. So what is the difficulty in this? So here, as I said, we have the noise current because of the resistor, like this is 4 kT upon R, and then we have the noise power because of the transistor, which is 4 kT gamma Gm, and then you have the 1 upon F noise. Anyway, it is already at the gate, so you can model it at the gate directly. So it is anyway analogous to the input referred noise, which is K upon W L C O X F. This part is anyway there, and then you can because of these two components you can figure out what is the output noise. So that is because this is your in, you can call it in r square, and this is your in 1 square. So the total output voltage at this point, or output power noise at this point will be given by simply whatever is the output impedance between this point and AC ground. So between this point and AC ground, we have seen that the effective impedance is RD parallel RO. We are assuming that okay, it is approximately equal to RO, or sorry, RD. So basically, we just get V out or Vn out square, Vn out square. This is equal to In1 plus In2 square into RD square, and then input referred noise because of these two components will be simply equal to Vn in square. This is simply divided by Gm square RD square, because that is the gain. So if this is the output noise, what is the input referred noise? The output referred noise divided by gain. So here we had discussed this concept earlier also, that if you are having say two independent noise sources, right? So last class we had discussed two independent noise sources, In1 square, In2 square, and then you are having a load resistor RD. Then what is the total output noise power? Just simply In for voltage. If it was voltage summation and these were voltage signals, deterministic voltage signals, then we would written In1 plus IL2 into RD is your output voltage. But in this case, it is a noise signal, so this is not valid. We rate In1 square plus In2 square. We have discussed the justification also, that why we sum up the basically the power. So IR square power. So in this case, sorry, I square, you can say in this case the power overall noise voltage over here Vn square, if I V out n square, n just denies there is a noise, so that is going to be RD square. So the same concept we are applying here. We are finding out the output noise voltage, and this is effectively the noise spectral density of the output noise voltage. So this, because this is also spectral density, this is also spectral density. These two are frequency independent, and if we combine the effect of this one also to find out output noise, then contribution of this one you can just multiply by Gm square. So we know that in order to transform this into an equivalent current, we multiply this guy by Gm square, and then it will just come another as another independent source in parallel with that, and then you multiply it by RD square to get the output noise voltage contribution because of this. But this is a frequency dependent spectral density, so this will give you the 1 upon f frequency dependency. So this is what the analysis is shown in that lecture. So what is the yeah? So any question on this?
The flicker noise is a voltage at the input, so we don't need to refer it, right? We can just refer the current sources.
Yeah, just for understanding that if you want to find out, just like you are having the other two current sources at the output. So if you want to transform this also and see what is the output voltage, output noise voltage, because of this one. So you can do that, and after that, the whole thing, the total expression is there, and you want to get the input referred value, divide by the whole, divide by the gain, and then you get the input referred value, just for uniformity. Yes. So any other question regarding this part? So here we have seen that okay, what is the effect of device parameters, like if you are increasing W by L or increasing the bias current, the GM changes, and if the GM, if it is improving, the overall input referred noise improves. And we have discussed the reason for that also, because the GM of the input device, even in the active load case, GM of the input device is helping in reducing the overall noise contribution, and that is because the GM of the input device is responsible for magnifying the signal also, whereas the GM of the load device is not magnifying the signal. It is therefore we can minimize the GM of this one, whereas the GM of the input device needs to be maximized to reduce the overall input referred noise. So this thing also we have discussed in that lecture. So I hope this contribution, like what is the role of GM, and also we have seen in that lecture, that if you have W, if you have to minimize the flicker noise, there again it depends on area. So W and L both have to be increased. So in order to get the GM, you have two options: either you increase W by L or you increase ID. If you increase if you increase ID, then overall small signal gain reduces, right? That we have discussed in this circuit. What is the expression of gain? GMRO, and overall it comes proportional to 1 upon root under ID. RO is 1 upon ID, and GM is root ID. Expression becomes proportional to 1 upon root ID. So if you rely on increasing ID for GM, the gain will basically go down. If you the other option is that, okay, you increase the W by L, and then in order to reduce the 1 upon F noise, you have to increase W and L both. So first thing is that, okay, you increase W by L to get a proper good desirable GM, so that the thermal noise is reduced. And then for maintaining that W by L ratio, you can still increase both W and L, so that the flicker noise is getting reduced, because flicker noise is dependent upon W into L, total area. So this is giving you a good thermal noise. And for a given W by L ratio, if you just increase it, this gives you good flicker noise for the input device, right? This is for the input device. Output device, we have seen that anyway, we have to reduce the GM. Increasing the L, for example, for this device will be reducing the GM. That also reduces the noise contribution of this device. So any question regarding that? This entire discussion on the small signal, also frequency response, and the noise analysis for active load and resistive load has been done in these two lectures. What I'm seeing is frequency response of the phase has not been shown. That's what I saw in that lecture. So that I will discuss briefly just to complete the picture. Yes.
So the like input referred noise, like we were getting one by RD term. So like means that noise is decreasing if RD increases, but like RD is we have higher resistance, the noise will increase. So and then justification was given that the gain also increases. But like so,
yeah, so English. So if you look at the input signal, so that is ultimately in that case the gain is dependent upon RD, and so if you are one side you are having the RD which is contributing to the overall noise in terms of root R, right? So if you're looking at the current or the voltage is 4 kT/R, whereas the signal is directly proportional to R, so that way you can say the signal to noise ratio will improve. So spectral density, it is Vn square is 4 kT/R. The input signal gets amplified directly proportional to R. So if you look at the ratio, that will improve. That's the idea.
Okay, yeah, okay, thank you.
Yes. Any other question?
Sir?
Yes.
Sir, while analyzing the frequency response using Miller method, you said that we won't be getting the zeros. So while plotting the board plot without using zeros, won't that analysis be it won't be appropriate? No?
Yeah, so this becomes more important than when you have stability closed loop circuits. So there zeros become important, and we need to take care of the zeros and their positions in the overall phase response. Open loop circuits, it still has effects, of course, because it will change the slope, etc. At certain points. But the speed limitation mostly comes from poles. So when we are talking about the speed limitation or the bandwidth limitation, they are analyzing poles in the open loop response serves sufficient, like at least the bandwidth that you can get from the open loop amplifier, that you can analyze entirely by pole. So zeros become more important for closed loop analysis. For that, of course, you have to first of all, you should know that where is the path of zero, which points will give you zero, and then in the exact analysis you can see that once you do the closed loop analysis, how those zeros will be changing. Those things we will discuss. So when you discuss the closed loop frequency response, we will look at the zeros effect. Even in the open loop, we can, in the phase as well as gain magnitude response, we can include that effect. So just wait for some time. Once we start looking at the feedback loop and the frequency analysis of the feedback loop, we will discuss zeros and also how to cancel the effect of zeros in operational amplifiers. Those things will come. Yes.
Okay,
Any other question? Okay. So let me just quickly, because I saw that phase has not been covered, so we can try to cover phase also quickly so that we have a complete picture. So I don't remember why I have not covered phase over there. And there are many other things also with respect to single-ended amplifiers that I would like to cover. Common source amplifier, I have not covered some other loads like diode connected load, or diode connected also had different kinds of diode connected. You can have NMOS diode, NMOS also you can have PMOS diode connected load also. So those things also we will discuss. Yeah. So let me quickly do the phase one. After that, we will go for the other loads. So phase response, it is also simple. Once we know that okay, this is how the magnitude response is working. Phase response also using the same argument. If I look at 1 upon S plus P1 and 1 upon S upon P2, two-pole systems. So two-pole systems, the phase response, if it is a say if it is a non-inverting amplifier, then of course it is going to be having minus 180 degree in each beginning. But common source is an inverting amplifier, so you will get a -1. So or whatever a naught is there, minus a naught. A naught is a positive number, and minus a naught denotes that to begin with you have a 180 degree phase shift. Okay. So now if you are starting at omega equal to 0, drawing straight lines here becomes a little bit of problem. Okay, so if you're starting with say omega equal to 0, so at omega equal to 0, once again we can see that okay, you will be at minus 180 degree. Overall phase shift is just minus a naught. So as compared to input, you are at minus 180 degree. So now if you go for so condition here is once again, last time also I think I took this condition, P1 is much less than P2. So you have P1 first, and then I think you can have P2 after that. I hope this was a condition. Otherwise, last time if I have taken reverse condition, doesn't matter. You can understand with respect to P1, P2 what will happen. So if you are going for this region, if your omega is in this region, you have omega much less than P1. So if your omega is much less than P1 as well as P2, you remain at minus 180 degree without any problem. So it will continue to be at minus 180 degree. Exactly at omega equal to P1, at omega equal to P1, what will happen? So this number is still very close to 0, because assuming that omega or basically P1 is still much less than P2. So even if your omega is becoming P1, the P1 upon P2 is negligible. So I can ignore the second term and I can continue with the first term. So second term still doesn't contribute. So now at omega equal to P1, what will happen? So here you are going to, this term is going to give you 1 plus iota in the denominator. So in the overall expression, it is coming 1 upon 1 plus iota. So in the magnitude, of course, we get 1 upon root 2. And in the phase here, it is e to the power of iota pi by 4, right? So, so here you have the magnitude and the phase. So you remember that an expression like this, 1 plus iota. I hope you understand that in complex number, you can write this as root 2 e to the power of iota pi by 4, right? This number, I hope you know this exponential representation of the complex number, e to the power of iota pi by 4. Now, if that is understood, then this will basically, in the numerator, it will become e to the power of minus iota pi by 4 upon root 2. So this root 2 effect, anyway, we capture in the magnitude plot, right? So in the phase plot, this is what is going to matter. So here we are getting minus iota pi by 4, right? So that means 45 degree. So you're getting a minus 45 degree phase shift exactly at P1. So this will cause further, minus 45 degree phase shift over here. So with respect to 180 degree, it will go down by minus 45 degree. Now, the moment you go far away from P1, now you are in this region. This region is omega, which is much greater than P1 and still much less than P2. So in this region, still I will continue to ignore the second term because omega is still much less than P2, only the first term. In the first term, also, ultimately, if you see, here you are going to get S upon P1, right? So S upon P1, here omega is much greater than P1. So I can ignore this 1 with respect to that. So I'm basically getting 1 plus 1 I can ignore basically because now the omega has become much greater than P1. So I can simply ignore this. And there I will get minus A0 upon iota omega upon P1. This is what I'm going to get. So iota is in the denominator. And then this iota basically, what does it denote? It is this can be replaced by e to the power of iota pi by 2. Because e to the power of iota pi by 2 is cos pi by 2 plus iota sin pi by 2. So you are basically left with just iota. So now this can again go in the numerator as e to the power of minus iota pi by 2. That indicates that in this region you are going to get it will saturate at this value, right? Minus 90 degree additional, right? So it will be minus 270 degree. So as compared to 180 degree, we have arrived at a additional minus 90 degree phase shift in this region. And then the same phenomena will happen. Now, as compared to this, if we look at the contribution of this term now, so till this point, whatever phase shift has occurred, after that, what is going to happen at P2? At P2, once again, the same phenomena. If I'm exactly at P2, this second term will become same, right? 1 plus iota is the S is iota omega and upon P2. So omega equal to P2, this will also give you exactly 1 plus iota. That is again give us this factor 1 upon root 2 e to the power iota pi by 4. That means again I will get a minus iota pi by 4 in the numerator, and therefore I can expect another drop. Now the thing is I will have to shift it up, or for the time being let us continue like this. So I will get only thing is I probably need to shift the axis down. So let me shift the axis down. So let me keep the axis here. So exactly at P2, what will happen? It will further go down again another shift of minus 45 degree, and far away from P2, again this give you another minus e to the power of iota pi by 2 term, which will mean that with respect to this point, another additional minus 90 degree phase shift. So if I look at this point, additional minus 90 degree phase shift, that means 360 degree overall, right? From this minus 360. So this is how the phase plot will look like if I look at two pole system. So, so this is what we should be aware of. This will be useful when we are doing the stability analysis in closed loop system. So both magnitude plot as well as phase plot we should be aware of. If you have zeros, the behavior will change. So if you have at any frequency, suppose you have 1 plus s upon z. Now it can be also 1 minus s upon z, right? Depending upon whether it is plus or minus, you may have a slightly different, effect in the phase, because if you have say minus s upon z, so you can figure out what is the magnitude, what is the sign of the phase. So depending on plus or minus sign, the phase will change. Now suppose I have a 0, which is much greater than P1 as well as P2. So this what I'm saying is this Z1, whatever 0 I have introduced in the numerator, Z is much greater than P1 as well as P2. So it's going to come somewhere at a very high frequency. So generally, even in the common source amplifier that we have discussed, this is the scenario. Generally, this Z we can see that okay, it will come at very high frequency. Again, it's not in some circuits it can come earlier also. So if that is the condition, then what is the role of this? Now, after you have reached this condition, minus 360 degree, what is the role if the sign is 1 plus s upon z? So if it is 1 plus s upon z, what is going to happen in the numerator? So s, again, if you look at exactly omega equal to z, that means omega equal to at the 0 frequency, which is much higher than the poles omega equal to z. So again, you are getting 1 plus iota. That means now it is giving you e to the power iota pi by 4. Now this term basically means that you are going to get, first of all, the magnitude is also root 2. So it is enhancing the magnitude. So the magnitude plot will go up. Whereas in the phase plot also you are seeing that now this term is adding the phase. So at this point, it is supposed to go up now because it is u of iota pi by 4. So it will go up, and then far away from it, it will become, if your omega is significantly greater than z, what will happen? You can ignore the 1, and therefore you are left with iota omega upon z, which is basically giving you a phase of iota pi by 2. So it will basically increase the phase, right? So again, it will go back to the previous. So this is the effect on phase plot. If it is opposite minus z, then you can figure out it will just having the opposite effect on the phase, right? Magnitude effect will remain same. Phase will be opposite. It will reduce further. So this effect of zero and pole, given a set of zeros and poles and their relative positions, where are they located? Assuming this, right? This is of course an assumption which basically lets us draw these plots easily, that omega is much less than p2, much greater than p1, and omega much greater than z. So this much is an assumption. Of course, in real circuits, you may get a condition where the poles are sitting close together. Like if suppose p1, p2 are very close, so what will happen? You will not get this kind of flat region in the phase response, right? Likewise, in the magnitude response, if here you are getting, suppose p1, p2 are far away. So suppose this is p1, this is p2, and if they are far away, then okay, here you get a clear minus 20 dB per decade, and then after p2 you get a clear minus 40 dB per decade. So there's a clear distinction because these two poles are far away. If they become very close, what will happen? So it will get mixed up. Suppose p1, p2 are like this. In between itself, you will get a maybe somewhere in intermediate value, maybe minus 30 or whatever. And after that, immediately after p2, you will get minus 40. So it will be some intermediate value because these are coming close together. So you're not going to get a clear distinction between minus 20 dB per decade and minus 40 dB per decade. It is a merged kind of plot. If they coincide exactly or very close, then directly you will come to minus 40 dB per decade. Right? So those kind of changes you should be aware of. What will happen if the poles are too close? So how the plot will change. So this concept that getting a board plot, phase as well as magnitude based on your pole and zero location, you should be able to do. This is important for stability analysis in closed loop amplifier circuits. Any question on this? Yes, any question? So some other things that I have not covered in that one, maybe I will try to cover, like some other load conditions I can quickly try to cover, and probably we can have some assignments started on those. So before we go forward, I think the third lecture in this one that I have given you, 7, 8, 9. So 7, 8, most of you have done. The third part, as I see, is frequency response of the active load. And there also, like, what I can see is the similar thing that I've discussed, and also the noise response has been discussed. So this, once you go through, I think things will be clear. I don't think there is much. So of course here there is some sizing issue mentioned that okay, W by L, GM, etc. GM of input device needs to be increased, and the GM of load device needs to be reduced. So once you go through that, things will be okay. And after that, the differential part has been started. So before I go to differential part, even for this common source amplifier, let us discuss some other configuration quickly, because they may be useful in circuit design concepts and you should be aware of that. So I will still wait for one more minute and see if there is any question regarding whatever we discussed so far in the two lectures, 7 and 8. 9, very few people have done it so far. 5, 6 people only have done it. So 9, I'm not discussing right now. Maybe that we can take up in tomorrow's class. But 7, 8 lecture and whatever I discussed just now here. So on these parts, if you have any question, let me know. Yes, any question before we yes, no question. So let me go ahead then. So I hope I'm audible to all of you. So we started with 30 people around. Now it has dropped to 24 people here, and there are some people over here in the Google Meet. So I hope everybody, those who are attending, they are present in the this place. Anyway, so so we have not discussed, I think, the diode connected. So in your basic electronics, sorry, analog electronics, you must have come through some other loading configurations, especially the diode connected one. So given this circuit, you should also be aware that, okay, what are the gain, bandwidth issues. You can also have load like this. This is a PMOS. You can also basically have a, this is rarely used, but you can find in certain cases that, okay, you have a condition like this. This can be some bias or it can be VDD also. And then you have NMOS. This is much more frequent. This one is less frequent. And then you can have other configurations which are kind of mixed, right? You can have this, and you can also connect some current source in parallel. This is VV. So so I call this, say, configuration 1, 2, and 3. So in configuration 1, what is the so I need to find out two things. One is the gain, second is the bandwidth, and third is the swing, so signal swing. So in case of the configuration 1, what is the gain? Case of configuration 1, what is the gain? Yes, quickly. Have you studied this configuration in or BJT version of this configuration?
Yes, so this is minus GM1 times RO2 parallel 1 by GM2.
Yes. So I hope you people can draw the small signal model for this one. The first one, if I draw the small signal model, what is it happening? So I had asked this question, I think, in the class also. So looking into the drain, looking into this, MOSFET's gate or drain, because here the gate and drain are sorted together. So if you're changing the drain voltage, the gate voltage is also changing by same amount, and the source is fixed. So basically, we are changing the VSG of this MOSFET. If you're changing the VSG of the MOSFET, conceptually itself, without doing the small signal analysis, you can understand that RO effect is going to be much smaller as compared to the VGS effect, because VGS has much stronger dependency. So here, since you are changing the VGS directly for this MOSFET, if your output is changing, output signal is changing, voltage level is changing, the VGS of this MOSFET, or in other words, VSG of the PMOS itself is changing. And therefore, in order to find out what is the effective impedance contributed by this, I will look at the ID VGS curve. So if this is your ID VSG, for PMOS, we can write VSG, ID VSG. So I will look at this and I will figure out what is the slope, because ultimately here we are changing the VSG, and for that, how much change in ID will happen. So if the VSG changes by a certain amount, delta, what is the change in ID? So the inverse of this slope will give me the impedance looking upward, R up. So generally, by solving this kind of amplifiers, we look at both the R up and R down, right? Because ultimately, this is going to be a parallel combination, because in the small signal AC analysis, what happens, this also becomes AC ground, this also becomes AC ground. So in the small signal AC analysis, we are applying the signal at the gate of this transistor, and it has its own RO, and then we need to figure out what is the load connected. So R down is simply the RO of this transistor, the channel and modulation resistance, and R up is the impedance offered by this diode connected device. So conceptually, at least we can understand directly from this graph that it is going to be 1 upon GM of this P. And if you want to do it in a small signal analysis form, so there also we can draw, there is no problem. So gate and drain are connected. So in this PMOS, the small signal model remains same for PMOS. So GM, VGS, and we have the ROP, right? GMP, you can call it if you want to specify. GMP and ROP, and the drain and gate are connected. So the drain gate are connected, and the source is at the VDD. So source is at AC ground. Now, in order to test the impedance, what is the impedance? What is the process? I apply a either I apply a small voltage signal VT and find out what is the current flowing IT, or I can do the reverse also. I can find out, I can apply a small signal current and I can find out what is the which is the drain gate shorted together. I'm applying a VT. So what is going to be the IT? First thing is that whatever is the VT is same as VG. So this thing will be simply VT because GMP VT, right? So this is GMP VT, and then you have this path. So the total current is IT is equal to GMP VT plus VT upon ROP, and therefore what is my input impedance? R up is simply VT upon IT. So this is going to be 1 upon GMP plus 1 upon ROP. Now in general we can say that ROP is going to be much higher. Now again, this is an assumption which sometimes may not be true if your GM is very small, bias current is very small, or your device size is very small. But in general, if we assume that this approximation is valid, ROP is much greater than GM, because here we say that okay, this slope is in general for a given MOSFET, this slope is much higher as compared to the IDVDS slope. So if unless the current is too small, we can say that okay, means in general this RO given by the IDVDS curve is much higher than this GM given by the IDVGS curve. Therefore, we can ignore, and therefore we are left with 1 upon GMP, right? And in that case, we are simply going to have GMP for the upper transistor. So I can replace this whole thing simply by GM 1 upon GMP, and then we are left with the lower transistors. The lower transistor anyway, it has also got its RO. We can ignore that also just with the same logic. Of course, here you see for the upper transistor, it is easy to ignore and justify, because for a same transistor, we can say that okay, RO will be much higher than GM. But here we're talking about two different transistors. It is possible that the GM of the upper transistor, or basically the GM of the lower transistor is not so high, or basically the RO of the lower transistor. For example, suppose the bias current of this one um, happens to be higher, and the channel length happens to be very small. So in that case, maybe the RO will not be negligible. But again, we are taking a general consideration that we can ignore RO with respect to GM. So in that case, this will also go away. And therefore, you just have a common source amplifier with a resistive load where the RD has been replaced by 1 upon GMP. And therefore, the gain is simply GM1, which is GMN, you can call it, into GMP, sorry, upon GMP minus sign. So this is the gain. I hope this is clear for all of you. This is the gain, GMP, GMN upon GMP. Any problem with this? What are the advantages of this configuration? First thing is, what is GMN upon GMP? In this configuration, the bias current is same for both of them, right? So GM, if I write down exactly in terms of say the values of the W by L. So we know that GM is 2ID mu n COX W by L. So in this case, anyway, these parameters are same. Mu and COX are same for W by ID is same for both of them, and the mu and COX may be slightly different. Mu and COX and mu and mu P COX. So ID mu P. So mu P may be different. COX we can still assume that okay, both of them are having oxide thickness which is same. COX also remains same. So this is W by L of N, and this is W by L of P, and ID is same in this configuration. ID remains same. So basically, only ratio is W by L and mu P. If I assume that okay, mu and mu P is just a constant ratio, you call it whatever root mu r, ratio of mu1 and mu p. So then we have a dependency on W by L of n divided by W by L of p. And therefore, we can see that the dependency on bias current and VT, there is no dependency. ID, there is no dependency. VT, threshold voltage, ideally, there is no dependency. So in a simple common source amplifier, we had discussed the issue that there is a lot of dependency on bias current, which in turn will depend upon VT. And since the VT when vary over temperature, process, etc., the bias currents will vary, and as a result, the gain will also be very sensitive. In this case, however, we are having ratio W by L ratio of the NNP, and also there is of course the ratio of mu1 and mu p. But assuming that okay, even if the mobility changes, they will be changing by similar amount, similar ratio. So with temperature, this may not change too much. This is a ratio of the mobility. So if I ignore this, then we have a good case that okay, the gain is fairly independent of the temperature dependent variables like ID, VT, etc., and solely determined by the W by L ratio. So we can get a more deterministic gain. So at any stage, if you suppose want to get a gain of 2, exactly 2, or gain of exactly 4, whatever, 3, if you want to get a good, ratio, deterministic gain, this is one way of doing it, right? Because here, if you want to get a gain of 2, I will simply make the W by L of the NMOS 4 times higher as compared to the PMOS. So I will get a ratio of 2. And likewise, I can keep on increasing the ratio. So in terms of gain, this is a more deterministic gain, which is dependent upon process, right? So this is less dependency on process and temperature. There may be some dependency on temperature because of the mu factor, but it is much more stable. And the second thing is bandwidth. So bandwidth point of view, what is the bandwidth of this circuit? How will you find out what is the bandwidth of the circuit? So based on our earlier discussion, what do we say about the bandwidth?
So this also will be like two, like we'll have our signal and we'll have the CGS1 on the input side.
Yeah, so
and also that Miller's theorem, that Rutherford capacitance also.
Yeah, so Miller theorem, yeah, it is there, but again here, because the gain is relatively small, here we are not having huge gain. Maybe if you want to get a gain of 4, you have to have 16 ratio. If you want to get a gain of even 16, you need to have a 256 ratio in the size, which is going to get difficult as we go beyond 10. So maybe up to 10, you can at max, you can assume that okay, there is you can achieve a gain of maybe 10. Beyond that, very difficult, because you can't have such a big skewed ratio. It also starts creating problem in the layout, etc. So suppose you can get a gain of 8, and for that you have a 64 ratio between W by L. Still, as compared to a common source amplifier with active load, this gain is lower. You are talking about at max 20, 30 gain, a few tens at max. So generally, it may be good if you are limiting yourself between a gain of say 2, 4, 16, etc. So or that order. So of course, Miller effect will be there, but because the overall gain targeted in this design is also smaller, so that Miller effect will also be relatively smaller. And second thing, even without doing the small signal analysis, so if I Miller effect will become important, of course, if you have an input source impedance, which is generally the case. Nothing is ideal. So whatever source, whatever previous stage is there, it will also have its output impedance, and therefore the net capacitance at this stage is important. And this CGD is going to contribute to that, and that is still experiencing Miller effect as in the previous design. So that is true. But the only benefit is okay, gain is anyway in this configuration, it is less. So this Miller effect also may be less pronounced. What about the output node? Output node, what can we see? Output node, what is the impedance? So no net impedance at this node, because we need to see after breaking down from Miller effect, we can break down this CGD into two components, and we have the net. We need to find out the net capacitance, the small signal capacitance between this node and ground, and net small signal resistance between this node and ground. So what is the net small signal resistance between this node and ground? Remember the concept, right? So we are trying to arrive at this kind of situation where if you have multiple stages, multiple nodes, each node, if we find out that, okay, this is the net R equivalent and C equivalent at this node, between this node and ground, then we can simply, write down our expression in terms of uh, the C equivalent and R equivalent. The pole will basically be determined by C equivalent and R equivalent. So I can figure out simply that what is the pole. So in this case, between this point and ground, because this is the input of the amplifier, this is the output of the amplifier. So at the output node, what is the net R up? What is the net R equivalent between this node and ground?
R up parallel R down.
So that is simply equal to 1 upon GMT. So this R up parallel R down is at the output node, R out equivalent approximately equal to, of course, this is R up, which is approximately equal to, in this case, 1 upon GM. Because R down is RO, as compared to that GM, 1 upon GM is much lesser. This is what the value is. So we said that this is a low impedance node, low impedance. So whenever we have this kind of nodes where you have direct connected transistors, at that point, we will get an overall low impedance. And the impedance is low, 1 upon R equivalent, C equivalent will also be high, because this R equivalent at that point is low. So for the same C equivalent or similar value of C equivalent, this pole will be shifted to higher frequency. So therefore, at least at the output node, whatever pole was coming, that will be shifted to a significantly higher frequency. So therefore, this is at least the output node is the speed limitation will be at least a little better as compared to the original design, because the second pole has been shifted towards higher frequency. What about swing, input swing? If I look at this device, or basically first let us look at the output swing. So is the output swing better or worse as compared to active load?
Better.
If I ask you to calculate, the output swing of this particular stage, how will we do that, and whether it is better or worse?
So we only have a lower limit. We don't have any upper limit now, because the upper one is always in saturation. We have shorted the gate and drain.
Think about it a little bit better. Upper limit, low limit means what? You can go to VDD or VDD point, 1.2 VDD or 3 VDD.
The low limit would be like the bias voltage you're applying plus V threshold and.
No, the upper side, you are, of course, this PMOS transistor, you are having source is connected to VDD, and lower side you have this condition. Now this is VDD, and this is whatever VG N you have applied. This is for biasing from previous stage, whatever VG is coming, that is the voltage. Now what is the V out? In this case, V out min. V out min is what? Allowed V out min. Quickly.
VGN minus VTN.
VGN minus VTN, because if you go below that, this transistor will be entering to triode region. So if your output voltage is going below VGN minus VTN, the M1 will enter into triode. What is V out max? Maximum allowed voltage of the amplifier.
VDD plus mod VTP.
VDD plus mod VTP.
So here the gate and drain are short circuited, right? So it will always be in saturation.
So if it is 1.8 volt and this is VT is 0.4 volt and this signal is going 1.9 volt, so it will work.
Gate is 1.9. Okay. And source is 1.
So you need to keep it. If it is going to subthreshold region, then it will turn off and it will enter into subthreshold region. There the current equation is different, GM equation is different. If you are operating it in super threshold region, we would like to make sure that it is not turned off. So in this case, if the moment the VT becomes much lower, the current will change drastically. This will turn off almost from whatever bias current you had. As compared to that, the bias current here will go down drastically. So many of the assumptions that you had in the design is no longer valid. So this ratio that you were having GM1 upon GM2, W by L1 upon W by L2, those all considerations are gone if it is turning off, right? So still you can say, okay, this is operating in subthreshold region, but the design equation that you have, W by L1 of the transistor M1 by W by L of transistor M2, and simply GM1 by GM2 cancelling out all other parameters, that will be no longer valid, because beyond the value of VDD minus mod VTP, the upper transistor will enter into subthreshold region, and then those equations that we had for the GM will no longer be valid, VTP. So the max value is this. So in general, if you had the current mirror load, there what was the condition? There, whatever is the VG, which is basically, this is your VDD, and you have some VSG drop. So VSG in general, you will have some overdrive, of course, and especially because the W by L of this one is pretty low. In order to get good gain, we were trying to keep the W by L of this one low. So VSG in this case may be sufficiently greater than VT. So we are assuming that VG is significantly maybe lower than VDD minus mod VTP. And then in this case, the load, the maximum output voltage, V out max for the current mirror load is what? This is going to be VG, VG plus mod VTP. Because as compared to the gate voltage over here, if the drain voltage goes higher than mod VT, then this will enter into triode region. For PMOS, the drain voltage should not go higher than gate voltage plus mod VT, that we have discussed earlier. So now this VG is less than VDD minus mod VTP. So here, therefore, overall, you can say that the max voltage over here, VG, if this is VDD minus mod VTP, slightly lower than that, and this is another mod VTP. So if you look at, if you compare these two cases, because here VG is, if I assume that VG is close to this number, that means the overdrive voltage that you have is relatively small. Suppose VDD is 1.
So we can't hear you.
Yes. I'm not sure. So Google Meet people, are you able to hear me? Hello? Yes, hello. Are you able to hear me? Okay. So in this case, what is the value? So here, if we have 1.3 volt, 1.3 plus, basically mod VT. So it can go to 1.3 plus almost 1.7. Whereas in this case, you are getting limited to VDD minus mod VTP, which is 1.8 minus say 0.4, which is basically 1.4. So you can see that generally this case you will have higher swing, because you are able to go to VG plus mod VTP, whereas there in this case you are limited by the VT. So whatever is the VT, you can't go beyond VDD minus mod VTP. So looking at some of these practical numbers, we can say that means you may get a significantly better swing on the upper side in the case of current source load as compared to the diode connected load. Same is true when you look at differential amplifier with this kind of load. Differential amplifier also you can have this kind of diode connected load, and also you can have this kind of current source load. So from the point of view of gain, I told you what is the benefit. From the point of view of bandwidth, I told you that okay, output impedance here it is low, therefore the pole at the output node is high. But in terms of swing, definitely you are getting a disadvantage, because the moment you use diode connected load, upper side swing will be getting limited. Is that clear, all of you? Any problem?
So it means like
Okay.
in the current source load, we are getting higher output swing, but we are how, sorry, for the diode connected line, we were saying that we are getting lower output swing, but we're getting more stable gain. That's the trade-off, right?
Yes. Yes.
Okay.
And
for the current source, it was we are getting the higher output swing, but the gain is not stable.
yes.
Okay.
So here the DC bias point at the output is not stable. So single-ended common source with this kind of load, you can't even you can't use it practically. You just simply use this kind of configuration. It is not possible because you need to bias it. Is that clear? So now in analog circuit lab, generally sometimes we do this kind of experiments. You might not have done it. I'm not sure. So this is, if you want to use current, if, for example, what will happen now? This is not an integrated circuit. So let us not discuss this. It will confuse you unnecessarily. So we are already out of time. Already you guys have spent maybe 3 hours. So I will not take much more time from you. Maybe let's look at the second. So this one, what will happen? So there's just the similar thing, but this particular, I told you that this is hardly used in some application where there is some certain requirement or some special cases, it may still be used. I will tell you exactly what is the benefit of this in future classes. There are certain special circuits where this may be useful. But here also, what is the gain? What is the impedance looking into the source of this MOSFET? Gate is constant, drain is constant. Gate, drain are shorted. And we are looking into the source of the NMOS.
RO parallel
Same
1 by G.
1 upon GM, say call it M2, and this is M1. So this is 1 upon, this is up, because ultimately what is happening, same, this is even easier to understand. Gate is constant, drain is constant, source voltage you are changing. If you change the VGS, what will be the change in current? GM VGS. Therefore, the impedance is simply 1 upon GM2. This, I don't even need to draw the small signal model. So impedance looking into the source of a MOSFET where the drain and gate are at constant potential, it is very easy. It is simply 1 upon GM, because gate is constant, drain is constant. Change in source voltage will lead to GM VGS change in current. So 1 upon GM2. And then I can simply replace by 1 upon GM2. Same thing applies, right? Small signal remains same. Frequency also, the frequency response argument, whatever I mentioned for this one, remains same. What about swing? Swing part, what is the situation? What is the maximum swing?
So your lower one is just VGN plus VTN. VGN minus VTN for the M1.
That is same. So the lower one remains same, and then the VDD, it is there. So here also, ultimately, if you look at the swing, if you're going, say, towards the higher value, and you assume that overdrive voltage is not very significant, it is still small. Again, here also similar condition will appear, because you don't want to turn this off, and therefore you have whatever VDD you have to stop at VDD minus VT. So upper swing is in this case also VGN or VDD minus VT. Because ultimately this is VDD, and then you have to basically get the maximum voltage over here is going to be VDD minus VT. So expressions remain same, but here also we get to understand that, okay, the impedance is almost similar in both the cases. The frequency response is similar in all the cases, both the cases. And in terms of swing, this is the scenario. This one has some additional effect in terms of inductive peaking that we will discuss later. So it has some disadvantage that will become clear in later classes. Right now, let us. So this one, the advantage is that you will not have the mu and mu p ratio, right? So this mu and mu p that you were getting in that one, that is gone. Here it is basically just W by L of the NMOS and PMOS. So in that point of view, it is even more accurate as compared to the W by L of the NMOS PMOS, because there at least this mu and mu p dependency come into picture. Therefore, temperature dependency will be slightly more. In this case, it is mu and mu n, both of them. Therefore, that mu and mu p is also gone. So it is much more, even more stable than the previous one. So that way it is having.
So
Yes.
But here the gain will be lower, right? Because mu p is typically lower than mu n. So we would have had a positive number in the previous one if we had used a PMOS. But here it is just mu n, so then we'll have a slightly lesser gain.
Gain is determined by GM1 by GM2.
Yes,
So
so
ultimately,
mu n,
I want to maximize GM1. I want to minimize GM2. So GM2, if you have to minimize, what is the problem?
yes, so GM2 in this case it would be mu n, so that would be slightly higher.
No, that you have other quantities, right? So W by L is there, so you can minimize that. So there you have enough number of parameters. W by L you can minimize. That ratio, of course, you have a higher mu n, but that can be taken care by W by L. Not such a big disadvantage. It has some issues related to inductive peaking that we will discuss. And also at this node, in terms of capacitance, if you see, there also you can figure out what are the, if I ask you to find out the capacitive contributions of the two devices at the output node, I hope that also you can figure out. So CGS, you can see, CGS will come here, and then you have the body potential, which is also, if you are connecting to VDD, then CDB will come into picture for the upper device, and likewise from the lower device. The same thing is happening here. CGS of this PMOS will come into picture, CDB. So if you are asked to find out exact expressions for the poles using the small signal capacitor model, those things you can do. The other one that I have drawn over there is intermediate version. Let us go through that also quickly. How many people are there? Because I'm too late, so maybe many people might have left. 20 people are still there, so I can continue a little bit more. So the third one that I had drawn was this one. This one, which is also simple to analyze, not a big deal. So based on whatever we have discussed so far, you can quickly figure out what is the gain of this configuration. This is current source load, VV, and this is direct connected load. This is your, if you had only, say, forget about this region, right? So if you had only this part, like this particular current source load and the current over the input device over here, then we know the gain. And likewise, if I forget about this one and I say that okay, only this part is there, then also I know the gain. But now combined together, what is the gain? How do we find out?
So like we label them, like the lower one is M1, left one is M2.
Let us call it M1, 2, 3. All we need to do is see the lower part remains same. All we have is a change in the upper RO. R up has changed. R down is anyway same. And once we find out R up, that is done. So what is R up in this case?
RO2 parallel RO3 parallel 1 by GM2.
So for M2, we have basically, if we can ignore RO2 of M2, because for the same MOSFET, we can say that, okay, RO2 is going to be much higher than 1 upon GM2. So the M2 will contribute as 1 upon GM2. This transistor is contributing 1 upon GM2. This transistor is simply RO because we are looking into the drain of the PMOS, with gate voltage and source voltage constant. Therefore, this is going to be 1 upon RO2 parallel this one. Now here there is a reason why we can intentionally create a condition where you can have still RO much greater than GM. So if I assume that RO2 is still much greater than, RO3. If I assume that RO3 is still much greater than 1 upon GM2, so the gain will remain almost same as before. A still remains GM1 upon GM2. So what is the advantage? What are we doing? Why do we use this? If I assume that still RO3 is much higher, and then the gain is remaining GM1 upon GM2, is there any advantage of this configuration?
The swing, I think, will be better now.
Why it will be better?
Like for the current source load, we had seen the upper swing. Like for V out max is better.
What do you mean? You have this one still present, right? This is not gone. This guy is still present, right? So still you can't go higher than VDD minus mod VTP. So what is the benefit? If you have two loads connected together in parallel for swing, which one will you consider? The one which is limiting. In this case, we will be limiting. Limiting will be this guy because it's still the same VDD minus mod VTP. This is allowing you larger, but if you allow this one to go larger, this one will be gone. This will be in off region, which you don't want. I want both of them to be in saturation region. So I will, if you have to look at the V out max, I will see the min of V out max because of M2 and V out max because of M1, right? So whatever is the lower of the two, that will be my V out max. So this is allowing me, 1.8, and for this one I can go as high as 1.7, but this one is not allowing me higher than 1.4. I have to go to 1.4. I can't go higher than 1.4. So that is not the advantage. What is the advantage? What else?
So the drain current of transistor 1 is much higher in this case.
So
So like we can increase GM1.
yeah, so if you have read the Radhavi chapter, I think second chapter or third, whatever, common source amplifier chapter, where all the single stage amplifiers are given, I think third chapter. So there they have explained this one also. So intentionally, what I can do is, if I am having ID flowing in this one, I can size or I can bias this transistor so that it carries max amount of ID, or larger portion of ID is being taken away by this one. Suppose it takes away 0.9 ID, and this one is left with only 0.1 ID. So I can set this VB so that this is taking almost 0.9 ID, and this guy is left with only 0.1 ID. So now in the GM ratio, earlier the ID was getting cancelled from both of them, right? Now ID will not get cancelled because now you are getting a ratio in this two transistors. Earlier the same ID was flowing, but now you are getting a ratio because of this also. So now you are getting a ratio of 10. So GM1 upon GM2, already you have a ratio of 10 because of ID1 by ID2, right? So this is coming because of ID, GM1 upon GM2, you have ID1 by ID2, so that gives you root 10, and then W by L ratio. So that will basically reduce the pressure on this W by L ratio. So earlier, now this is going to give you something higher than 3 already. And then if you want to get another factor, maybe if you get it 4 times, you will get 2. So gain of 6 coming just by keeping this factor of 4. Whereas in earlier case, if you had to get 6, you need 36, right? That is the advantage. So this circuit, we can basically get higher gain while reducing the sizing constraint. And if you reduce the sizing constraint, then what will happen if your W by all of this one is lower, then the input capacitance, Miller effect, everything will be lower. So the bandwidth will also be better. Because in this case, the impedance over here remains same, almost 1 upon GM net impedance. But if you look at the bandwidth input node over here, the net capacitance will be significantly reduced for the same gain, because this guy doesn't need to be so large now. So the input capacitance, Miller effect, all will reduce. So therefore, the dominant pole will go towards higher frequency. Bandwidth will be improved. So these are the two benefits of this configuration. Is that clear to both all of you? Yes. Any question on this?
So the bandwidth part, can you repeat once?
How are there 4 presenters, attendees? I don't know how is it happening. I have not made any presenter, but there I can see 3 presenters, and these 2 people have become
removed, sir. Like so I was making like all everyone attendees, like if you have to make, because
anyway.
students removed.
So fine. So yeah. So what is so what I am saying is this part is clear, right? So you don't need a large W by L for M1 if you use this configuration, because you can achieve a large gain just by sizing, right? Sorry, just by diverting the current of M1 into M3. So here I am taking away 0.9 ID into the M3, and this guy is left with only 0.1 ID. Therefore, GM1 upon GM2, anyway, we are getting a root 10 factor. Is that clear?
Yes, sir.
And then we have, therefore, the W by L required for the M1 is smaller, and if the W by L is smaller, CGS, CGD, all the capacitance basically of M1 will be smaller. Is that clear?
Yes.
And if that is smaller, then the Miller effect will be smaller, input CGS will be smaller. That means the dominant pole contributed by this input node will go towards higher frequency. Is that clear?
Yes.
So this thing you should keep in mind. Maybe, yes.
Like we are doing this like parallel current source to improve the gain without changing the ratio as well, like W by L ratio. But so like that will improve the bandwidth. But then we also said that for reducing the total noise, we have to keep the bandwidth as less as possible, like the minimum requirement, so that it is integrated over a smaller bandwidth.
That is a different, that depends on application, right? So if your signal itself is high frequency, what will you do? So you need to cater to the signal bandwidth. So whatever is the signal bandwidth, you need to meet that. Then comes the noise consideration that, okay, how much, you can't say that, oh, because of the noise consideration, I will limit the bandwidth. Bandwidth is decided by first signal requirement. Then you can minimize after that. So this one basically clubs the advantage of both of them, the current source load as well as the diode connected load. This is first of all giving you stable DC bias point, because if you had only the current source load, you will not get a proper DC bias point at the output. This diode connected load is helping you in getting proper DC bias at output. That is one advantage. And second, this current source is helping you in reducing the sizing constraint on the M1. That is helping in increasing the bandwidth. So that is also another advantage. So as compared to only higher, a much more stable DC bias point and a deterministic gain. Overall magnitude of gain may be still lower than what you can get only using current source load, but a stable DC bias, clear deterministic gain, and then higher bandwidth. Is that clear? So once you know that, okay, how do you calculate the bandwidth of a circuit, looking at the nodes, figuring out what is the impedance over there, what is the small signal capacitance over there, you can figure out what is happening to the speed of the circuit, which node is going to contribute to the bandwidth limitation, which node is critical for the board plot. Those things you can analyze. So here we can see that this node anyway, we are still having low impedance because R up is 1 upon GM. Therefore, this node is not going to be so critical. Whereas input node, we had a Miller capacitance, etc. So now by the help of this current source, the Miller capacitance will be reduced. Therefore, it will enhance the bandwidth. Without even drawing the small signal model and doing the board plot, looking at this circuit, I can make some comments on the bandwidth and the gain and the DC bias, all those things. So this things should be clear to you. So for every circuit, I don't need to start doing the small signal model, drawing all the parameters, and then looking at the expression, derive the expression. No, not required. So once you know that, okay, these are the critical nodes in the circuit, what is the impedance over there, what is the capacitance over there, we can figure out the behavior, how it is going to be. Any question? Same thing will come on differential amplifier also. The differential amplifier, you can also have similar kind of approach. Load, you can have combination of these two. All those things you can have. Any question before we conclude? I wanted to teach only maybe half an hour just for doubt clearance, but again, because these parts were not covered in that lecture, so I thought, okay, let us complete. So any question before we conclude? How many people are left? Let's see how many people have that much patience. 14, 15, 16, that's all. 16 people less have left. Okay. Any question before we conclude? Okay, fine. So I will have to take this kind of approach where there is a mixed mode approach. Some part I will ask you to look at the video lecture. Some part we will discuss here so that we can proceed faster. And based on today's discussion, probably I will think of some kind of assignment, I will let you know. I will post that assignment with some description so that you can do something. And then for tomorrow, whatever video lecture you need to see, I will let you know. I think for the single-ended, we still do not have, we haven't covered common particular lecture that I have shown you there, you don't have all those stages covered because there I directly jump to higher level topics. So still probably tomorrow's I will cover some topics related to common gate, common drain, uh, and then we will go ahead with the differential amplifier. And probably I will, once you go to differential amplifier again, those lectures are there. I will ask you to go through some of that initial part, and then whatever additional is needed, I will cover through that. So if you combine both these, online, offline, this recorded version versus this one, it will help me in speeding up quickly and finishing, covering more theory quickly, so that we are in a position to start with some project activity early enough. Because right now your basic, the analog circuit course, I think a lot of things are missing, a lot of things have not been covered. So I have to take help of some previous recordings to, will bridge that gap. So make sure that when I'm asking you to go through some lectures, please go through that ahead of time. I will see if I have to ask you to take any recording, I will send you that information before 11 a.m. so that you can go through that. And then we will have the doubt clearing session. Probably I will do it in the evening time, regular 5 p.m. onward, 5 p.m. to 6:30. And then we will wind up. Okay. If you don't have any question, let us conclude. Thank you.